In this video, we'll create a wireless personal area network between two nodes and analyze the throughput. It is a personal area network for interconnecting devices centered around an individual person's workspace in which the connections are wireless. It permits communication within about 10 meters, which is a very short. Various in-home applications driving the need for communication. So, some applications demand low rate, low power consumption protocol stacks. Hence, we define IEEE standard 802.15.4. It defines the protocol and compatible interconnections for data communication devices. It uses low data rate, low power, and low complexity short range radio frequency transmissions in wireless communications. This standard defines the characteristics of the physical and MAC layers for low-rate wireless personal area networks. ZigBee, which we use in this simulation, builds upon the IEEE standard and defines the network layer specifications and provides a framework for application programming. Now, MAC layer. It's one of the two sublayers that make up the data link layer of OSI. It's responsible for moving data to and from NIC, which stands for Network Interface Cards, to another across a shared channel. MAC layer uses MAC protocols to ensure signals sent from different stations across the same channel don't collide. IEEE PHYs provide the capability to perform CCA, copying collision avoidance, in its CSMA-CA mechanism. This protocol reduces collision and improves the overall throughput in wireless personal area networks. A station in CSMA or CA contends for shared wireless medium by employing a binary exponential backoff. This PHYs require at least one of the following three CCA methods: energy detection over a certain threshold, detection of a signal with IEEE 802.15.4 characteristics, or combination of these methods. Now we discuss about the theory. First of all, the packet transmission begins with a random backoff, a number of slots of 20 symbol duration, sampled from 0 to 2 power MAC minimum backoff exponent -1 followed by CCA. CCA failure starts a new backoff process with the backoff exponent raised by 1. 2. MAC minimum backoff exponent +1, which is lesser than the MAC maximum backoff exponent. When the maximum number of successive CCA failures for the same packet is greater than MAC maximum CSMA backoffs, the packet is discarded at the MAC layer. A successful CCA is followed by the radio turnaround time and the packet transmission. If the receiver successfully receives the packet that is without any collision or corruption due to the physical layer noise, the receiver sends an acknowledgement after the radio turnaround time. A failed packet reception causes no acknowledgement generation. The transmitter infers that the packet has failed after waiting for MAC acknowledgement wait duration time and retransmit the packet for maximum frame retrieve times before discarding it at the MAC layer. Theoretical analysis. Here in the simulation we set the application layer payload as 70 bytes in node 1 properties, and when the packet reaches the physical layer, various other headers gets network layer header which is of 28 bytes, transport layer header which is of 8 bytes, MAC header which is of 5 bytes, physical layer header which is of 6 bytes gets added when the packet finally reaches the physical layer. We have to consider that the application layer payload should be of 70 bytes, because if the packet size at the physical layer is greater than 127 bytes, it gets fragmented, and because of overhead bytes added, we set the application payload as 70 bytes. NetSim uses unslotted CSMA or CA, and so a packet transmission happens after random backoff and followed by CCA and turnaround time, and is followed by turnaround time and acknowledgement packet, and each of them occupies specific time set by the IEEE standard as per the timing diagram shown. Random backoff average is given 3.5 slots, CCA is given 0.4 slots, turnaround time is given 0.6 slots, packet transmission is given for 11.7 slots, and then Turnaround time is given 0.6 slots followed by acknowledgement. Now we calculate the theoretical throughput. The symbol time is of 16 microseconds. Each slot is having 20 symbols, and therefore the time for a slot is 0.32 milliseconds. The random back-off average is of 3.5 slots, which is 1.12 milliseconds. CCA is given 0.4 slots. Turnaround time is given 0.6 slots. Packet transmission time is given 11.7 slots. Turnaround time is given 0.6 slots. Acknowledgement packet time is given 0.6 slots. And hence the total time is of 5.568 milliseconds. This, if we calculate the application throughput, we get 100.574 kilobits per second as a throughput. Now if we compare this with the simulation result, we notice a slight difference. It's because the average of random numbers generated for backoff need not be exactly 3.5, as the simulation is run for a short time, and also in the network layer DSR protocol is running, so root setup process will take some time.
Now that we understood IEEE standard 802.15.4, we now create the scenario for wireless personal area network to see if simulation result matches with the theoretical result. Double click on NetSim Academic, select Simulation, Personal Area Networks, Zigbee. Create the scenario with the help of wireless nodes and personal area network coordinator. Change the property of nodes to meet our requirement. Maximum number of retry of the source is 7. Transmitter power is 1 dBm. Now check whether remaining properties satisfy our requirement. Beacon mode of PAN coordinator is disabled. In application properties, change source ID to 1 and destination ID to 2. Run simulation by taking simulation time as 100 seconds. Note down the value of simulation throughput. Change the simulation time to 10 seconds. Change the simulation time to 50 seconds. Change the simulation time to 200 seconds. Compare simulation results with theoretical results.
As we discussed earlier, the simulation result is different from the theoretical value. Simulation value approaches the theoretical value by increasing the simulation time. Simulation throughput is 100.408 kilobits per second. Theoretical throughput is 100.574 kilobits per second. As the simulation time is increased, the throughput reaches the theoretical value, is seen from this table.